So this is week 2 of our workshop. In the first week, as a recapitulation, we got an overview of the deep learning field. It's a broad field. It can do a lot of things. We can do natural language processing. We can do image processing, right? And we could do, deal with tabular data and so on and so forth. And we got a flavor of that, a very quick flavor of what it is. After that, I talked about the way we are going to approach this course, which will be a little bit non-traditional. The traditional way is you start with the fundamentals, then you move on to CNN, and then maybe RNN and LSTMs and time permitting transformers and so forth. The way we are going to do it is we will start from the cutting edge so that we become useful rapidly in our labs. So we'll emphasize transfer learning, in other words, benefiting from other people's work, trained models. They are very applicable. Increasingly, these models are very, very powerful. You don't need to build a neural network from scratch and train it. Very, very often, you can just take those models and just apply it to your problem with great efficacy. So that is transfer learning. The other problem that we have in machine learning is we often have a lot of hyperparameters. Now, to recapitulate, hyperparameters are those things that you can't train a machine to pick up, to optimize on. Machines optimize during the machine learning process. They optimize on the parameters, but not the hyperparameters. So we have to do a lot of search, grid search, randomized search. These must be techniques some of you may be familiar with. I call them the basic techniques. But now the state of the art has moved forward. You cannot do grid search or randomized search. Grid search, because combinatorially it's not feasible. So suppose you have 10 dimensions or 10 hyperparameters, and each of these, even if you pick 10 values in, you're looking at 10 to the power 10 possible combinations of the hyperparameter. And you can't be making 10 trillion models. It is just not feasible. So we now have more powerful mathematical techniques to search the space of hyperparameters and even architectures to find the best hyperparameters. That is called hyperparameter optimization. And often when we deal with neural networks, because one of the hyperparameters sort of implicit is what possible neural architecture should we take? How many layers should there be? How many nodes there should be in each layer? Right? How many short circuits we should have? Which activation function we should use? What should be the dropout? What should be the regularization? Now I'm using words that you have, most of you don't know, but you will learn in due course of time. But take it as a fact that there are lots of decisions to be made when we craft an architecture. It's almost like making a building. You have too many choices. How many rooms? Which room will face which direction? Which will be adjacent to which? An analogy of that is in neural networks. So there are almost infinitely many ways you can design a neural network. Given that fact, the question does arise that in this vast space of possibilities, possible architectures, how do you find the best architecture? And that topic is the neural architecture search. Neural architecture search is the state of the art these days. And it is being used everywhere. I'll give you an example. When COVID started, it started around, should we say roughly speaking, November, December. Right? When it started, and now of course we have evidence that it might have started actually in early 2019. There are all sorts of scientific evidence for it, but we'll leave that aside. Let's say that most of us woke up to the fact that there is COVID in November, December. When we did, very early on, people started applying deep neural networks to decide whether it could tell, looking at a lung X-ray, if somebody has COVID. To their great surprise, they found that yes, you can do that. Some companies in Taiwan and South Korea, etc., they even tried to commercialize it. Some research groups in India also looked at it. And the problem was, it was not able to beat the state-of-the-art accuracy that would be there from a chemical test. Like for example, when you do RT-PCR, reverse transcriptase polymerase chain reaction, quite a mouthful. It's an elaborate process that takes about 24 hours. And in US, if you go for a test, the results typically come out in 3-4 days. But nonetheless, it is the state of the art. We realize that it's not the best at this moment, in the sense that it still misses out 20% of the cases. It gives 20% false negatives, and it gives 5% false positives. Not a nice thing, but that's the best we can do. It might have improved in the subsequent months. I do not know, but I'm quoting results that may be a few months old. But when we tried to do it with a deep neural network, people found two interesting observations. First is that they could do it. It was close to the state of the art, but it did not beat the state of the art, which means that there is scope of improvement. Now the question arose, why did it not beat the state of the art? Two reasons popped up. The early architectures were sort of trial and this and that, which was remedied with neural architecture search, and we'll come to that. And the other big reason is there is just so little data on this disease. Catching hold of X-rays in vast quantities to train a deep neural network is hard. It's a data problem, not an architectural problem. And that is it. So now there is an open source initiative. There is an architecture called COVIDNet. We will discuss it in one of these Sunday sessions. It's an open source project now, so everybody can contribute to the research of COVIDNet. What it does is it looks at your lung X-ray, and literally in the blink of an eye, it can tell you whether you do have COVID, whether you have some other lung problem, or your lungs are perfectly healthy. So that is a positive thing. The not so nice thing is that it does not beat the state of the art accuracy, mostly because we have not fed it enough data. And data is still hard to come by. It's one of the problems. Every single researcher in COVID, as you know, is sitting there begging for data. But it will take time. It's a new disease. It will take time for data to gather. So, but if you look at the COVID architecture, you will be absolutely amazed, COVIDNet architecture, you'll be absolutely amazed at how complicated it is. And one look at it and you know that it could not have been just done by somebody sitting on a drawing board and thinking up a neural architecture. It could only be done through a neural architecture search, coupled with experts then tuning it, changing it a little bit, and adding things to it and so forth. So it has to be a collaboration between neural architecture search and experts guiding it. And that is the state of the art we have on COVIDNet. So if you guys Google at COVIDNet, you'll find a research paper and you'll find a set of data. I would love to see somebody take that up as a project for this workshop. You might end up making a huge difference to humanity. See if you can improve upon that neural architecture from the things that you learn here. So, well, that is about automated machine learning. You can do automated machine learning by hyperparameter optimization in the case of, or by neural architecture search, or by something called meta learning. Learning how to learn. How does a neural network learn? It studies how it learns, or any algorithm studies how it learns. So there are all of these areas. There's a lovely textbook that I have added to our book section. It's absolutely free and available on the internet, Hutter's textbook. I highly recommend that you folks, as you get interested, glance through it. We will cover it in depth at some point in time. So that is transfer learning. Now, the last thing that I will cover in considerable depth is this whole problem of explainable AI. As more and more machine learning models become complicated, their accuracy goes up, but they become completely unintelligible. Why is it making these predictions? We don't know. It is hard to trust that because we do not know the biases in the data, not because we don't trust the mathematics, but because we don't trust that there is no bias in the data. Data always has subtle biases. I gave you the example, the story of the military and the civilian versus military vehicles. That story is much talked about in this community. I don't know if it is true or not, but it certainly has a message. Biases are hard to find. The other real case was that of the facial recognition with the facial recognition service that Amazon opened up. And it had deep bias if that had been used by law enforcement agency in practice. Far more number of Afro-Americans would be behind bars for no reason, absolutely no reason at all, because they would be identified as rapists and serial, murderers and so forth. So it is as terrible as that. So much as we celebrate the power of deep learning and deep neural networks, the cautionary tale here is when we master this, with these tools, we can not only do a lot of good, but we have a potential to do catastrophic damage. And so in this workshop, you will see that from a very technical perspective, I will be talking about explainable AI, which is a hot topic. Explainable AI not only further ensures that you don't have biases or subtle biases, it also furthers understanding. Suppose one example that I can give you is, I talked about Kepler. Kepler took the data from Tycho Brahe. Uh, Tycho Brahe was Kepler was an astronomer who's famous. Almost everybody has heard of Kepler. Not many of us have heard of Tycho Brahe, who was his mentor and his teacher. Now, Tycho Brahe was doing astronomy, gathering data, before there were telescopes, sitting in his, on his roof and looking at the skies. And the skies are best looked at in winter nights. In Europe, the winter nights are not exactly pleasant and warm like Indian nights. They are very, very cold. So, so Kepler used to be there, and from the way I heard the story, he was a brilliant mind, but also not exactly looking forward to being on the roof on cold winter nights. So Tycho Brahe would occasionally nudge him to be there. So in any case, as Tycho Brahe passed away, all the logs, the astronomical logs of data about stars came to Kepler. So Kepler then painstakingly, and you could genuinely say in many ways that Kepler was the first data scientist in a very genuine sense, because he pored over the data for a very, very long time. And there's a very interesting history to it. Some of you, if you're interested, read a wonderful book called Figuring. It is written with sparkling language. Just the language is a pleasure to read. There's a book that came out very recently, actually, Figuring, a year or two ago. The first chapter is on Kepler. It's also available as an audiobook. Just listen to the first chapter and you'll get a sense of the life of Kepler. And it's a pretty tragic life, actually. The orthodoxy put Kepler's mother, declared his mother to be a witch. And she was practically imprisoned and spent her life there. And if I remember right, she was either burnt at the stakes or he managed to save her from being burnt at the stakes, so she died in prison. So he had a pretty tragic and sad life, but he made tremendous contribution, and very painstakingly he did that. So when he did those contributions, he not only could predict where the stars would be or where a planet would be, which is the prediction problem. Looking at the data, you build a prediction model in modern language. You can build a black box model that will say, look at this part of the sky and you'll find the planetoid, or you'll find this planet or this, whatever it is that you're looking for. But what he did is he discovered the Kepler's laws of motion. Right? And I'll talk about the two laws, one being that all the planets have elliptical orbits and the sun exists as one of the focal points. The other being that in unit time, each planet sweeps out exactly the same area, irrespective of where in the elliptical path it is. Right? These were the two Kepler's laws. Now, if you think about the latter and ask yourself, can an artificial intelligence discover these laws? The discovery of the laws further understanding. It takes the frontiers of knowledge forward, astronomy forward. But just having a black box prediction model, it does serve in predicting, it has practical utility, but has it really furthered human knowledge? And if you think really about it, a plain and simple answer would be perhaps not. Right? And so when you go and ask the black box model to explain itself, The hope is that you can find interpretable analytical models that explain it. And that is one of the big areas of activity these days. We are going to do this as part of this course. And lastly, of course, we'll do all the traditional stuff, the fundamentals, the neural architectures. Now the neural architectures are a zoo. There's so many neural architectures, but we'll cover the dominant themes in this workshop. As we go through part 1, part 2, part 3, come December end, hopefully you'll celebrate in Christmas, not just your Christmas, but you'll celebrate uh, having mastered a fairly wonderful discipline. So that was the summary of last week. Last week we had a quiz, 2 quizzes, week 0 quiz and week 1 quiz. I noticed that the week 0 quiz participation was quite a bit. Week 1 participation was a bit low. So I would encourage you to go finish that quiz on your own. Of course, by now I've posted the video solutions to those quizzes. Lab work, please do the lab. Many of you have done the homework and posted really wonderful pictures on the Slack, and we can see how well these neural networks are able to identify them. You see both the strength and the weakness. For example, this neural network is not able to recognize faces. Why? Because for privacy reasons, it has not been trained on people's faces. It is not able to learn about things that are completely strange to it. For example, you show it an iPhone, iWatch, as one of you did. I think Prachi, you did. And you notice that it sort of comes close. It says it's a watch,
yeah,
right? And so forth, but it cannot say specifically it's an iWatch because it has no notion of an iWatch.
yep.
So that's sort of, that was that. The last is there was a weekly survey. Guys, please do fill the weekly survey. This is how we make sure that the quality of the workshop stays high. Every week, I do carefully listen to read the survey results. Based on the survey results, if I find that on certain topics, many of you were confused, I make it a point to repeat it, either in an extra session or on the next week's theory session. So do please take these reviews seriously. If you haven't filled it in this break, please do take out time and fill up the reviews. All right, folks, so that finishes the review of week 1. Now, I would like to go on to the topic of this week. And let me share my screen for that purpose. Any questions, guys, before we start? Which screen are you folks looking at?
Week 2 plan. Today we are covering universal approximators.
Wonderful. So you are looking at the right one. Sorry, for some reason it does. Yes. Okay. So let us get started. This is the plan for week 2. Did you guys see the plan for week 2? I posted it both on the website.
Yeah, got your email too.
Yes, you got an email and it is there on the Slack messages. So gradually, guys, I may stay with just Slack because it's a bit of a time-consuming thing to remember to post at both the places. I hope by now all of you have subscribed to Slack. If you have not, it is really look into your mailbox. You would see an email inviting you to Slack, and please do join it. If any one of you are not part of the ML 400 channel, the deep learning channel, do please let me know. We will fix it during the break. So our plan for this week is, the theory session is, we will understand the concepts, the core concepts behind deep neural networks. The lab will, in general, it will sort of resonate with the theory, but it will cover a slightly different set of topics. What we will do is we'll build our first deep neural network from scratch. Quite literally from scratch, and we'll see how we do a deep neural network. What goes into making or writing a deep neural network? Then we'll learn about how to create a data set, prepare a data set. The way you do, for example, in ML 100 and 200, you would do it using pandas, data frame. So what is the equivalent of data frame in PyTorch? And how do you load data and give it to the machine? Because here, one of the concepts is you need to load and give it data because the data may be vast. And this is generally true in deep neural networks. The data sizes are ginormous, usually huge. If you just look at the amount of data that has gotten downloaded onto your machine, you'll realize that a lot of data gets used in training these deep neural networks. So that will be the PyTorch. We will also do a blog reading, and this will be the first entry into reading research papers and things like that. So the first reading will not be a research paper, but it will be a blog. It is Christopher Ola's blog. He works at Google Mind, the Google Brain, I believe, I forget which one. So in the Google Research Group. And he's written a wonderful blog, which I've added to the course website. If you go to the course website, you will observe a few things. Let me show what you will observe. You'll notice that there is a new section here. Are you guys able to see? There is a new section here. Let me make it even bigger. I hope you can see neural nets are universal approximators. This will be one of the topics we'll start with today. And these articles that you see are really very good. So the reading material for this week is that there is a YouTube video and there are two blog kind of things. This is your reading material for this week. The original papers are a little bit hard to read, but those of you who are interested, you should pay attention to the original research paper. But I would say that if you don't read those papers, there is no harm done. Much of what the papers say is already there in these two articles. One article will cover today in the lecture itself. And there is a YouTube video. If you don't want to follow the article, you can just watch the YouTube video, which is very interesting actually. So this is the plan for today. So, and for this week rather. Now, coming back to where we are, I'll get started with the theory part today. We'll cover three topics. One of them is universal approximators. That word sounds rather grandiose, and what it is, we'll discover. The second is the activation functions. And the third one is something called gradient descent. Now, some of you may be familiar with gradient descent. We have discussed it in every prior workshop, but there are people who are not familiar with it, so I'll review it in any case. Okay, all that being said, I'll start with this big question that you see on my writing board. Why are neural networks so versatile? How is it that a neural net can do language translations, can recognize music? You know, you just play a bit of music and it will recognize what that music is, what that song is, or who the player is, and so forth. Right? It can write poetry. It can do neural, the paintings we saw last time that it could paint. It can do all sorts of things that you wouldn't imagine it would be capable of. Today, it is almost able to drive cars and so forth. It can fly drones, it can do all sorts of unthought of things, right? And we live in the world of AI. AI is, in a very genuine sense, it is the new electricity, and it is eating the world for lunch. Everywhere you notice, every single field is being permeated by that. So I'll start with something, and now we'll start going deep into the technical material. So I'll start with this question. Why are neural networks so effective? Why are they so versatile? So when you think about this, the way to go about thinking is this. Suppose, and here we'll think about it mathematically. See, your input data, whatever it is, let's say that you have the size and the volume of an animal, right? So it's your X vector, which is made up of X1, X2. X1 is the size and X2 is the volume of the animal. And so this is your R square space. And what you want to do is you want to predict, let us say you want to predict two things based on the size and, okay, one thing, let's say, based on the size and the volume, maybe let's not take, let's take children. Suppose you know their size and their, well, weight, height and weight. You want to determine what is their age. So age is a real number. Whichever way you map a point from here to here, a point to this, and another point, let us say, to another point, let's say here, to that maps to, let's say here, nonetheless, you would agree that there has to be some function of the x vector, some mapping function that takes you from here to there. That takes you from here to, from the input space to the target space. And that is what I meant when I said that regression is a mapping from Rn, where data comes as n dimension, now to generalize, to R. So this is, in simple terms, what a regression is. Now, there are a few caveats to that, and I'll come to that in a moment. By the way, do you notice that I'm writing R with the unnecessary bar to it? That means this R stands for the real number line. So when you say R square, you're basically, so for example, e.g., R squared is essentially one real number line that you may call x1, another real number line going perpendicular to it, x2. And all these real number lines will axes, as they are called, real number lines or axes. They will always be orthogonal to each other. Right? So in three-dimensional space, of course, you can imagine a third direction, x3, going perpendicular, x3 minus x3, minus x2, minus x1 in this direction. Right? So you can imagine a three-dimensional space, and then from there you can generalize. So if data comes, roughly speaking, with n columns in a very intuitive sense in a spreadsheet, n columns, and the n plus 1 column is the target space, then you're basically saying, how can I read the, in a row of data, how can I read the values in the n columns and use that to predict the value in the n plus 1th column, right? That's essentially what regression is. So to do that, you always think of it as some function that you don't know. That is it. You have to find a function. Now, how do you find that function? We'll talk about that. But before we talk about that, a little bit of a caveat. See, I always say that the target space is a scalar, right? Scalar here, generally. Let me use the word generally. But it's not always true. I sort of oversimplified things, and I suppose for once I should mention it. See, if your target space is, let's say that, let me just give examples of target space. Target space is wind velocity, right? The velocity of the wind. Now it is more complicated, right? So what you're doing is you're predicting velocity as a target space, and this you would realize is made up of two components, v1, v2, isn't it? Velocity along north-south, or maybe east-west, more like along, let me do this, along east and west, and this is along north-south axis. The velocity at a given point right? So you can ask this question that suppose I give you a lot of weather data. I tell you all sorts of conditions, parametric conditions that are there. Now, can you, based on the input, find a function such that V is some function of input data, right? Are we together, guys? So the target space sometimes can be, a vector, right? So it can also be R, from Rn, you are going to Rm, right? So so m dimensional vector. So this is an illustration, but I won't use this example to keep it simple. Just think of regression as going from n-dimensional space to a number, because that's simple. That's how we develop our intuition. But we keep in the back of our mind that, yes, something like this also could occur. Are we together? So now,
that's a fun question.
Yes.
Can we go to a higher dimensional space from a lower dimensional space?
Can we go to a higher dimensional space from a lower dimensional space? Yes. I'll give you an example. Suppose you're just in Fremont, approximately. Let us consider Fremont a point on a map. And I say you stay in Fremont, but you tell me the wind velocity as a function of altitude. So you realize that at this moment, I believe there's no breeze here. Right? It's pretty still and rather smoky. But if you climb up in the z-axis, in the height axis, what will happen? You will start seeing a wind blowing.
Right.
And so that wind will be a vector. And that vector is a function just of height, just of one, you are going. So in other words, let's say, let's write this case since you asked this. Right? So your question is, can we have regression where n is smaller than m, isn't it? This was the equation. And the example was, say in Fremont, you want to know, to predict wind velocity, not wind speed, but wind velocity as a function of altitude. And you can think of all sorts of other examples. But the fact is, yes, you can.
So we'll get three outputs for one input?
Yes, so if you even want to look at the wind, if you look at it, typically you look at it as along the north-south and along the east-west. So, you can say that the wind is blowing south-southeast with a certain velocity, isn't it?
I'm just trying to imagine what the function will be like. Because I can imagine like a higher dimensional function going to a lower dimensional function because it has a lot of variables in it.
No, but it is not hard to imagine. It's like, think about it this way. When you are doing from, let's say, a point altitude, let me just write altitude as x, right? When you write a function, what you're doing is you're writing f1 x is the velocity along the north-south direction, v1, and v2 is another function, f2 of x.
Oh, I see. So there'll be multiple functions.
Yes, exactly. The only thing is you'll co-train them. When you do the gradient descent, you'll do the joint gradient descent.
So can we have a function vector in this case?
It is the function, the ultimate function that you'll come up with will be a vector, sort of. It's a vector function. It has to be. Think about it. A scalar 1D suddenly went into 2D, right? 2D vector.
It has to. Yeah.
It has to. So this function has to be a vector function.
Got it.
Isn't it? I can give you many examples. So for example, a temperature gradient, think about temperature gradient. So imagine that you realize that we live next to the bay. Anytime we feel hot, we walk over to the bay. Well, it used to be true in the golden ages when we had fresh air, but let's hope it comes back. At this moment, we don't even know in California we'll get fresh air or not. But anyway, so what happens is that at any given point, what do you have? You have something like a temperature at a given point. Are we together? Right? A temperature. And so let me call temperature X is the X vector here. Now, at any given point, you have temperature, which itself is actually, let me write it in all its glory. Your input space is temperature at a given point. Right? And then you can find the gradient of the temperature. Right? Right. What is the gradient of the temperature? It says that, let's say that this is the bay. Right? And so if I go towards the bay, what is the rate of increase of T with respect to the direction towards the bay, right? B is the direction towards the bay. Likewise, I can have an increase in temperature perpendicular to it, orthogonal to the bay. Let me just call it O. Do you realize that even starting with something as simple as a number, by looking how it changes across this space, you can actually get vectors out of it. So therefore, you realize that gradient is a vector function. And as you will see, gradient is one of the topics we'll talk about today.
Thanks, Sas.
So this hopefully answers your question. So now,
yeah, it does.
Now that we realize that this is, guys, so these notes, of course, I'll give it to you guys. I'll post it to the class webpage. Assuming that this is true, let's simplify life. Like I said, always imagine things in one dimension. So let us say that all machine learning, we will loudly say we are doing an arbitrary many dimensions using our usual trick. But in reality, we develop our intuition first in one dimension. Right? So suppose y is some arbitrary function of x. So think of some arbitrary function. Does this look strange enough? Right? And it could be going below the axis also. So let me throw that into the picture also. It may be doing this. How about this? Just to illustrate the point that it goes in every direction and so forth. So let us say that this is fx. Once we realize that regression is the search for the best, the ground truth fx. So we say, let the ground truth producing the data. I keep using the word ground truth. Do we understand what that means? That real function of force that generated the data that we have, from which we are studying, isn't it? From which the machine is trying to learn. Being y is equal to fx. Now, this is the real fact. Given this fact, what is our job? We want to, the whole purpose is, we want to do something like, our goal. We want to find, actually, let me write the ground, okay, we'll leave it as that. We want to approximate it with g of x, right? Such that g is approximately equal to fx. Are we together? Now, what does this approx mean? It basically means that suppose I come up with a function that is here. Let me follow it up with some other line. Suppose I did something which was like this. What would you say about g? You would say g of x. Do you see what we are saying? G, would you call it a reasonable approximation of fx?
Yes.
Right, it is. And so the statement is that, see, you'll never discover what fx is, but you can make more and more high fidelity approximations to g of x. And how do we make that high fidelity approximation? We need some a way to quantify what does it mean to say it's very close to g, or it's very close to the underlying truth. And that brings in the concepts of loss function. So we'll talk about something, or rather quantify this word more into a precise language. Let me write it down. We will make our language more mathematically precise. And mathematics is just common sense encoded, so do not be worried about it. Mathematically precise. Okay. We'll do that. What do we mean? Language of approximation. Approximation. My handwriting is atrocious. So that is that. We can do that. But at this moment, let us say that we want to do G. How do we do G? And here, there is a mathematical theorem that is reason for hope. This mathematical theorem is just a beautiful result, actually, that came out many, many years ago. I believe 1989 or 91, 89, I believe. Right? So the original reference paper is there on the website. What it said is, a neural network with one hidden layer, can approximate any, and therefore, in mathematical language, and therefore, every function. So when you write y is equal to function, and by the way, I'm writing it in one dimension, but this is actually generally true. Even when the input space is multidimensional, it's n-dimensional space. Right? So it says that you can always find, a neural network will always approximate every function fx with some gx, right? With some gx, such that it's a good approximation. Right? So in what sense? We'll talk about loss functions and errors and so forth, but we'll leave that for now. Those of you who did ML 100 and 200 may remember some of it. So this is where we stand. So let me just summarize what we just talked in a moment. What we are saying is, let's go back. We are saying neural networks, they are amazingly effective. And we want to understand why they are effective and so versatile. But before we do that, we set up a little bit of a mathematical machinery. We thought about it and we realized that regression is nothing but, it is this. It is a mapping from n-dimensional input space to a scalar value. Well, that is not always true. Sometimes it's to a vector field, but we will skip that word for now. Keep it simple. So now, not only that, but to understand what is really going on, we will simplify the input space also and just take one-dimensional input space. And now we are all used to drawing curves and things like that since high school. So we end up in a situation like this. Here we are, right? Now the question is, the theorem is, so this is a theorem. And this theorem is called, this is literally the universe approximator theorem. So this theorem has gone through many refinements over the years. The original version that it came out, it insisted that you must have something called an activation function. So I'm jumping a little bit ahead, but forgive me for that, that it would work only in a special case. If your activation function was sigmoid. It was a sigmoid activation function. Activation function. And at the same time, you're talking about one hidden layer. Right? But then the next, let me just therefore call it approximation theorems. Right? So the A version was just very specific. The B version generalized it and said, it is actually not a property of the activation function, but of this architecture of the neural network. So long as you have a neural network like this, right? So this is y is equal to the g of x here. So this g will be a very good approximation to the fx. Right? And you can have a lot of hidden layers. This is, sorry, a lot of nodes in the hidden layer. So there's a very interesting thought to this actually. When the universal approximation theorem came about, people then asked that why do we need then neural networks with more than one hidden layers? All right, why, more than one hidden layer? Because the universal approximation theorem says that one hidden layer is all that we need. So I'm going to give you a hint. It is not just being able to approximate a function well, but it is also being able to approximate it fast enough and reliably enough. And so the other considerations that sort of justify why you should go for multi-layered neural network. In fact, the word deep in neural network refers to multi-layered neural networks. So we'll come to that. Okay? But hold that thought in your mind. I'll just state the facts at this moment. And then the last thing that came about is that, so it's a property. So i.e. the property of the network, property of the, people call this sort of network a feed forward network. And why they call it that, that too we will learn. So at this moment, we are introducing a lot of animals in the zoo that we haven't explained or understood. But before this talk is over, we will understand that. So we'll go through in cycles. We'll come back and review all this once again, once we understand those things. But we can't understand those things unless we give some foundation here. And then came the third version, or the transpose version, in fact, I will call it transpose version, which basically said that instead of creating a very deep neural network, you can create a network which in each layer, instead of creating one single hidden layer, which is giant, you could actually create multi-layers, right? So you could create a feed-forward network like this, which is already getting pretty complicated. So there we go. Right. And then, so you can go through a few layers, and then when you go through a few layers, and finally all of those things, whatever number of layers there are before the last one comes to the last one, this thing, this is X going in, and here you have Y hat. The predictions you usually make it where a Y hat is GX, the neural network is predicting. By the way, let me give you a little bit of a background on the hat notation. In this field, it is a convention that reality is written with X and Y and so forth. Is data, is the data that you get, observables. Predictions are distinguished by making them wear a hat. All predictions will wear a hat in this field. Okay? It's true all over machine learning. So this is it. So there are three versions of this universal approximation theorem. We won't go through all three versions. And in fact, we will just touch it from a very intuitive perspective. The proof of this theorem goes into really abstract mathematics, and we won't go there. At this moment, we will take it on faith that the mathematicians must have gotten it right. Okay? But we will rediscover it from a very practical and intuitive purpose, sort of an intuitive manner. And to do that, before we do that, any questions? Because now I'm going to start start with a motivating example. I will take two examples, one with classification And then the other would be for regression, which will come a bit later. But let's start with classification. But before I start that, guys, are there any questions?
So I have a couple of questions.
Okay.
First one is, why is this called a theorem? Like, what is a theorem? What does it mean? Because I felt that a theorem had particular rules which need to be, which if followed will result in a certain outcome. But here it seems like the outcome is dependent on, say, a certain property of a feed-forward network, and obviously there'll be different networks for different outcomes. And the second question is, why is the C part of the theorem called transpose version? What does
It's just
transpose
a
mean?
colloquial way. What you did is, instead of creating a very, one single layer, which is very, very tall, you sort of flatten it up into multiple layers.
Oh, I
So
see.
people who do matrices, they tend to look at it as the
Got it.
transpose. You have laid it flat,
Got it.
right? And when you lay a matrix flat on its side, you say that you have transposed it.
Hmm. Okay.
There is no reason. It's not an actual transpose. It's just sort of a colloquial way that people refer to it.
Mhm.
But now let me come to the first part of it. Is it a theorem? See, in mathematics, when we talk of, for example, the Pythagoras theorem, a theorem is something that is true if certain preconditions are true. Are we together? So, assuming that you're on a Euclidean surface, on a flat surface, then the hypotenuse square will be the sum of side squares in a right triangle,
Mhm.
isn't it? Right? We learned that in high school, right? Now, that theorem has certain preconditions. You cannot do it on a sort of a very, on basically on your blanket after you wake up in the morning. It's all wrinkled up. So that there it won't hold true. If there's a deformation, if you try to do it on a balloon, you might be disappointed. Right? Things like that. So you have to state what are the preconditions for something to be true. If those preconditions are true, that is why all theorems start with if, then this is true. If it is a right triangle, implicitly on a Euclidean surface, flat surface, then the hypotenuse square is the sum of side square. So now that is one aspect of it. It will always be true. The other aspect is this remarkable quality of there's a ring of eternity to a theorem. It is a truth that you have discovered that will last from now till eternity. It can never be undiscovered. You can never have a version 2. It's not like Windows, Windows 7 and then Windows 10. In software, we keep having different versions of the software. But it is the only thing that once discovered remains in the sphere of human knowledge. It is forever. Even physicists, theories change. There's Newton's theory of gravity superseded by Einstein's theory of gravity, which someday may be superseded by an even better theory. So theories come and go, but theorems are eternal. What I'm saying is about neural networks, the universal approximation theorems are theorems. They are not theories. They're forever there. Once you realize that they're true, and therefore they have to be proved. You need a proof of this. Theorems have to be proved. You must be remembering proofs of Pythagoras theorem that must have haunted you in high school. So likewise, this theorem has a proof. The proof is very sort of, I would say, let's not get into the proof because it's very complicated. You'll need Fourier series, Fourier transforms, and Banach spaces, and the sort of things we don't talk about in computer science or in engineering or in real life, basically. Mathematicians deal with them. But let's stress to the mathematician that they have rigorously proved this to be true, and therefore we know that it is true always.
So what are the preconditions? The preconditions are the function needs to be there needs to be a sigmoid activation function.
No. That was the initial version. So the B version proved that actually it has nothing to do with sigmoid. So long as you have this architecture, one single hidden layer, it will, irrespective of what activation function you use, it will always be true.
I see.
All right. And then came the transposed version, which is, see, these are enhancements to it. These are generalizations to it. The generalization says that you don't need just one hidden layer. You can actually have multiple hidden layers and it will still be true.
Nice.
Right? So this is, in some sense, the most generalized version of the theorem.
I see. But one hidden layer can do the job. You don't really
One
need
hidden layer can do the job. And in fact, there used to be a question at one time that before the deep neural networks came about properly, people used to hand construct a multi-layered neural nets. And there was a little bit of a tension, actually. I remember the history that some people would say it's a fool's errand. All you need is one hidden layer. Well, obviously, theoretically, that's true. In practice, as you will realize, reality is different. No? It's like the big O notation. Two algorithms may have the same big O notation, but one may still be 10 times faster than the other. So reality is a little bit more involved. And of course, today we live in the world of deep neural nets, which is the whole field of subject, the field of study for our current workshop. Right? So we'll do with that. So now I made a pretty tall statement. We are talking about a theorem, but how do we understand the theorem? We won't go through the proof, but there's some intuitive understanding is really worth it, guys, because it's at the foundation of deep neural networks. So I'm going to give you that intuition before we go to the break. Let's finish the classification before we go. So there is one example that I keep coming up with, which is a very contrived example. So think of it of educational or didactic value only. I don't think it's true in real world, but I'll imagine two kinds of fruits. One of those are blueberries, and blueberries are light and small. So this axis is x1 axis is, let us say, weight. And let's say this is the x2 axis, and this we will take as volume, right? So all the blueberries, small, big, whatever it is, they will occupy, let's say, this region of space. Actually, they will tend to have a more bell curve distribution. So I already know this isn't very accurate, but we will contrive this example. And then occasionally there'll be the rare big blueberry. And then let us bring about some other berry. Let's take cherries, right? Let's take a color more appropriate to cherries. What is a color for cherries? Well, maybe this. Let's take this, right? So let's say that the cherries are bigger and heavier. So they have a distribution like this. When you have data like this, I ask you this problem, write a classifier. Write a classifier. The problem statement is create a classifier that can associate given x1, x2, that is the x vector. It will map it to fx to what? A set of either blueberry, berry, or cherry. It will pick one or the other. Are we together? So now you say, well, I know one of the simplest ways we can do that is by creating something called using logistic regression. Do we remember logistic regression, folks? If you don't, just take it as a fact that it is a way of finding something called a decision boundary. So decision boundary certainly merits its own line and color. Would you say that if I drew a decision boundary, let me make it really thick. A straight decision boundary like this. Boundary. Then you can say that things on this side of it are blueberry and things on this side of it are cherries. Does this seem understandable, guys? that all we are doing is to create a classifier is equivalent to finding a decision boundary like this. Because if we have found a decision boundary, we have solved the problem. Isn't it, guys? Would you agree?
Yeah.
Yes, we have solved the problem. Now, if you look at this, this is a straight line, and some of you may remember that this, and again, if you don't, it's all right, you can review it, or if you don't know it at all, it's the first time you're encountering this, that is okay. Don't worry too much about it. It just so happens that this has a function. This distance from the decision boundary, d of x happens to be some things, some weight w0 plus w1 x1 plus w2 x2. Now, some of you may remember that I used to write beta naught, beta 1, beta 2 in the past. In the deep learning world, it is much more conventional to use weights. The word is weights. These parameters are weights. Weights. New name, or should we call it synonym for parameters? So if your distance is positive, you know that if your distance dx is positive, greater than 0, cherry. If it is less than 0, blueberry. And if you're sitting, if dx is 0, you're sitting on the yellow line, you're undecided. You can go either way, right? So that's your logistic regression. Now, when we look at this problem, just as a recap, what happens is that the likelihood that it is a cherry, so if you ask this question in a classic, like what is the probability that a given point is, and this is a review of the logistic, actually, let me put it next to the name, was log of odds, probability that it is a cherry versus the probability that it is not a cherry, the log of that is equal to the distance function. So you're saying that the log of odds that it's a cherry happens to be the distance from the decision boundary, right? That is all that the logistic regression equation is ever trying to say. And of course, this is conventionally also written in a more different way. People often write it as, in a more traditional way, you will remember, 1 plus e to the minus dx, right? Or people use z here. Let me just use z. And if you see z here, you would see it in this format. And well, x is obviously a function of z, but probability of x. And this is the equation, or this is the form in which you traditionally find this equation represented. I find this a little bit more intuitive because it means something in terms of this picture. So are we together, guys? This is just a quick review of how we learn to classify data. You need to find the decision boundary in the feature space, right? In the input space, you search for a decision boundary. The simplest is you start with a linear decision boundary. Make sense, guys? Any questions before we continue? Everybody is quiet. Guys, give me some feedback.
No.
Is this clear?
Yeah.
This is clear, right, to all of us. So we have all done this at some point, or we can do it. If you haven't done it, then sit with me and I'll give you a longer explanation. It's not mysterious. This is all it is. So the way you do that is quite interesting. Now I'm going to represent it in a very sort of an electrical way. Do you guys know what a rheostat is? Or a variable? Variable resistor, exactly. So what is a variable resistor? What you have is basically a coil into which you feed in electricity, and then you have a slider that can move back and forth. And this slider, the electricity continues from this slider, right? In, out. And so what happens when you move the slider in a rheostat or in a variable resistor back and forth, right? Suppose you apply a certain voltage. Suppose I have a voltage, fixed voltage. You know that the current, so there is a relationship in physics called V is equal to IR, right? The current voltage is current times resistance. Are we together, guys? Right? So in effect, you can control, given the same voltage, you can control how much current flows through by controlling the resistance here. Are we good, guys? Right? So suppose I want a certain, suppose the output current is what I look for. Y is the current, I. Input, so voltage is your X. Now what happens? Your Y, which is actually the current, is a function of X. What is X? Voltage. And how is it a function of voltage? It's actually a linear function of voltage. It is some weight, that is some resistance. It is voltage divided by 1 over R, some 1 over R times X, which is the voltage. Am I making sense, guys? Huh? Y, which is the current is voltage divided by the resistance, and this resistance I can play with. So you can ask this question, suppose voltage is fixed, but I want to get just the right amount of current. So how do I do that? I just slide the resistor and I get it. Does that make sense, guys? Is this intuition coming across?
Yes.
It's a very simple intuition. So now hold that thought in your mind. Now what we will do is, here is a mapping we'll do. Whenever we look at input data, sometimes think of it that these are actually voltages, and think of the output as some form, as a current, right? So see what happens. We are having this, now I'll just make this rheostat sort of like this, a box, or let me write it not as a box. Okay, maybe as a box. Imagine, so rheostats are usually square looking, so I'll write it as a square. Suppose you have X1 voltage coming here, and you control it. I'll call this W1, right? The inverse of resistance, which you can change. Remember, this is the slider we can slider we can use to change output, isn't it? And so your Y is the current from here, from this voltage, the current. Remember that. Let me write it somewhere in big letters so that the intuition remains with us. This is, Y is the current, the output is the current. Input, X are the voltages. So you say, well, this is good, but maybe I need to look at 2 voltages. Suppose I have another X2 here. Well, what can I do? I can take another little box, go purchase one more rheostat from Radio Shack. Oh, Radio Shack is gone, isn't it, guys? Is it still alive or is it completely gone? Anybody remembers about Radio Shack?
Completely gone.
Completely gone. Huh? Okay. So WT. So where do we go for a resistor these days, or a variable resistor these days? I don't even know. At one time I used to go to Fry's, but even Fry's seems to be on life support. So now what I will do is I have 2 boxes. What it will do, this will produce a little bit of a current of its own, Y1. This will produce a little bit of a current of its own, Y2. And suppose I have a way of adding the 2 currents together. What will I get? I will get Y is equal to Y1 plus Y2. I'm adding these 2 currents together. Am I making sense, guys? Are we together?
Yes.
And so now imagine that these things are actually all of this here. Now let's create our first black box. Well, here it's a purple box, but bear with me. Now suppose, let me move this a little bit up and create space. If this drawing looks small, guys, let me know if you have difficulty understanding. So now let's look at the pink box. The pink box, we don't care. All we care is that internally it contains multiple of these, two of these resistors or rheostats, variable resistors. All we know is that we are getting X1 and X2, and this is your weights, W1, W2. These are the knobs that you can turn. And output, and there is an output machinery of adding the results of these two and getting your current, Y, that is your current. These are your voltages. It's a very practical intuition. So now I tell you this thing, guys, that I have a table, right? And what happened is that when you bought this machine, it was beautifully tuned. For different input voltages, you could get different currents out here, right? But then you, because you obviously, you can't avoid the temptation of playing with rheostats, at least I can't. The moment I see rheostats, I start sliding things back and forth. As a kid, I used to do that. So you have screwed it up, right? So God knows where these resistors are pointing. So you have data. You used to remember that when the rheostat used to work perfectly, when this box, let's just call this box, magic box. When this magic box used to work perfectly, then it used to produce a certain amount of current, right? Voltages and current, right? So you have a table of this, some table, something. So you have a table of a lot of things. And now the problem that comes is, you don't know. This whole thing has gotten misconfigured, right? And you have to now, these sliders are at random position, these weights have gotten randomized, and your job is to fix this magic box. Are we understanding it, guys? So how will we fix it? We do know that this is that, and you know, Y is X1, W1 plus X2, W2, and maybe it also had a little generator of current. It would just produce some magically a current, which was it was some unit. There also, there is a W naught, and how much current you took from that depends upon it. So we'll add some magic here. You can ignore W naught, but just think in terms of these inputs. So the total current that comes out is this, based on whatever the value it is. And what you're trying to do is you're making this, somehow you need to restore it to its good configuration. And you know that there is a solution because, of course, when you got the magic box, you could. So how will you do that? There are many ways you could do that. For example, you could hold W1 fixed and then go about sliding W2 till you get the values correct somewhere. So, you know, you could take this row. Whatever the value of X1 is, X2 is, what you can do is just freeze W1. And if you play around just with W2, you might be able to come close to the real value of Y. And then after that, you might move the W1 around a little bit, slide everything a little bit till you get this one going. But the trouble is you got this one going, but the other ones won't be going. Right? So because data always has a bit of noise to it, you know, so there's some, okay, I should mention that. There is always a bit of noise. Data never comes perfectly. So you'll always get in real life, and I don't want to introduce a noise generator also here, but think of that this is producing some random noise too. So is this intuition clear, guys? Huh? And what you're looking at is this magic box is your regression box. Right? A regression box produces a line. Right? The relationship is a line. So if you have X1 or X2, then this equation will represent a plane. or rather hyperplane, a plane. If it was only one x1, then it would be a line. Huh? And in higher dimensions, x1, x2, because you're looking, actually, I should not draw it like this. The y will, it's a three-dimensional data. It is something, actually, why don't I do it a little bit below? We are talking about this. This is x1, this is x2, this is your y, or rather y hat, because now you're trying to predict or create the machine that will pretty much be as good as new, right? And so what will happen is there will be some plane. Now this plane, as you know, the equation of a plane is this, something like this, right? So regression, in this case, discovered a plane geometry. Geometrically, we discovered a plane, isn't it? And when you discover the right plane by tilting it in all sorts of ways and finally hitting upon it, you have solved the problem. You have a solution, or you have a model, right? And you may not get it exactly, you know. Your values may be close to the real values. They may not be exactly the way the magic box came from the factory, but you need to just get close enough so that it works. Are we together, guys? Huh? Now, that is regression. So to summarize, regression is when we do this, x1, now let's generalize it to xn, input, n-dimensional input. What happens is, think of it that each of these, they have certain weights along the way. So if you think of it as a box, and then what it does is it adds up the product of these two. And so what comes out is y, and there is an additional bit of weight coming in W naught. So what happens is the output is W naught plus W1 x1 to Wn xn, right? This is it. And the clearest intuition that I can think of it is as a box of rheostats, variable resistance. So when we talk of learning in machine learning, what does it mean in terms of our magic box? What do you think it means? Physically, what are we doing? When you say that the machine is learning from data, what is it trying to do? Anyone?
Figuring out the weights.
Exactly. It is moving the sliders here and there so that it is able to produce the original data or come as close to the original data as possible. Isn't it, guys? So that is what the process of learning is. Data is there. Think of it as the original thing. And now you're trying to approximate it. You're trying to recover that state, right? So we'll remember this. Now comes one more fact. For classification, you don't just do this. What you do is you take this output, and so here is our magic box. I'll put it as a magic box. It is made up of these weights, W1, W2, X1 goes here, X2 goes here. Now, suppose you do something. You create a distortion function here. So what you want to do is, typically the way you think of it is, you don't want it to be triggered. Sorry, I apologize. This is jumped somewhere. This is a touch surface, and it seems to be, oh, what just happened? Where am I? Compiler. I seem to have gone to a different page altogether. I apologize. Right, this is it. This is where we are. So sometimes what happens is you don't want to trigger something till a certain threshold is reached. So you want it to be, if the input, if the initial y that is coming out here or here is the, let me call that z actually. We always reserve the word y. So z is your w naught plus wi xi, multiplication of these, summed over all possible input dimensions. So what y is, and so this is your z. what you want to do is you want to pick a threshold. Let's say that the threshold is 0. And what you want to do is for small values of z, you want to ignore it. And then suddenly you want to do this thing that is called a sigmoid. You want to trigger action. You want to go from an off state to an on state rapidly, right? As a function of z, and then you want to saturate. When you do this, if you look at it, it is, think of S. And what happens if you stretch S? It becomes, this looks like this, isn't it? A stretched out S. So these, any function that has a shape like this is called sigmoid. Sigmoid function. There are many sigmoid functions, but the most popular ones I'll mention. The logistic function is the most common that people know about. Logistic function. Right? And then there is the tanh function. Tanh function. Then there is the error function, which is essentially the integral of bell curve. Definite integral of bell curve. So in other words, minus infinity to, for those of you who are interested, others can just ignore it, the bell of t. Bell being e to the minus t square over t, all the usual things that you have, 1 over 2 pi square root. Right? This is your bell. So there are many, many functions that have this shape. I invite you to go discover more of those functions. All of those functions are called sigmoid functions, and sigmoids are pretty much at the heart of machine learning algorithms, artificial intelligence algorithms. So, but why does it come in here? Suppose we add a distortion here, so that what comes out is a value between 0 and 1. And this value, why would that be useful? Suppose we could do that. Now, this sigmoid, for logistic case, what comes out, y, as a function of x, would be, what you do is 1 plus e to the minus z, where z of x, z being this thing. Right? So it's a bit of mathematics, don't have to go into it. Think geometrically, it just distorts your input to something else. Yeah, input curve to something else. Now, why is that useful? It turns out that this describes, with a certain cutoff, this is actually describing your classifier decision boundary. Of course, this must be familiar to some of you. Let me come here. And this is a review for many of you. This is it. The yellow line that you see here and this equation, as you know, now you see that this equation is the same. Y is the probability of it being a cherry. Right? So now, how does this relate? And I'm quickly coming to a break, but I will take this, before we go to the break, I'll leave you with a puzzle. You realize that using a straight decision boundary, straight logistic regression, which we all have studied, right? We are able to, using logistic regression, which I can do using this fancy box of resistors and that distortion function. Those distortion functions have a fancy name. They are called activation function. Why that strange word, activation function? You say that when something achieves a value of 1, it sort of is waking up, right? It's coming, it's getting active now, it's doing something, right? It's getting to the active state. That is why this sort of functions that you apply, these distortion functions, are called activation functions. So anyway, using logistic regression, the point is we can draw linear decision boundaries. This is a summary of where we were going to, boundaries, right? using logistic regression. And how does a logistic regression look in terms of physicality? It looks like this. First is this bunch of weights, W1, WK, WN, and then this distortion, activation, this activation box, right? And then finally your output, right? And here goes your X1, X2, X3. This is traditionally represented in a more abstract manner, or what people represent it as is this node. They will say that this is this is the distortion part. They usually don't make it square, but they do it like this. And they will sort of stick this resistors as though they were in the path here. They'll take it out. So you have X1, X2, X3, so forth, W1, W2, W3, and then you stick in one more, it's called the bias term, if you remember, and then output. This is your Y hat of the X vector, right? X vector given these values of W. So when a machine is trying to look at data, suppose you have data X1, X2, X3, and Y, right? Or for example, whether it's a blueberry or not, which is probability of this being one or the other, let's say, it is actually using this box, essentially. And the lesson is it can draw a linear decision boundaries. But now comes an interesting question. Suppose our data comes like this, and in the interest of time, I'll make a simpler diagram. Sorry. Suppose you have data, actually this is not wide enough at all. Suppose you have a data where the decision boundary is like this. I'll just draw a decision boundary. So that this is all blue, let's say. And now obviously blueberries and cherries will probably not make sense unless there's some weird genetically modified variety. Something like this, right? You have two classes, red and blue. So let's use the word red and the word blue here. You still have your input space like this, space like this. So now you say, how can I draw this V-shaped decision boundary? This is the question, right? The question is, how can we draw this decision boundary using the box that we have? That is a question. And assume that you can buy in the, your Radio Shack just has a lot of these boxes available, or not Radio Shack, or whatever the hardware store is, electronic store is these days. Well, I suppose it would be Newegg. It's an online store. So, well, whatever it is, you can buy a lot of these boxes, this logistic regressor, regression kind of boxes that will help you do that. So now the question for you is, how would you do this? Anybody would like to guess? Guys, anybody?
You make
Maybe the
two lines.
of the first one.
Yes, so one thing you could do, very good. Why don't you articulate it? Say it in full words, sentences. What would you do?
I think there
So-
were two answers.
Yeah, go ahead.
Go ahead, Rafiq.
No, I was saying since we already have an equation for the first one that is going down, then if you just inverse that, then you and use another node with the inverse of the first one.
No, so I'll make your life a little bit harder. It would be hard to inverse. I will make this curve like this. So in other words, convert it. Then what? Still, you're on the right direction, Rafiq, you're on the right direction. But say it, what would you do? What can you buy to make this work?
So you have essentially two lines that you're creating. So you need two boxes.
Excellent. So maybe with two boxes, we might be able to get away with it, isn't it? So what you can do is, suppose I take one box here, right? Let me use white here, yellow, because the decision. So imagine that I use one box here. This corresponds to this line, right? And I use another box here that corresponds to, well, this line, right? So you realize that these will draw decision boundaries like this, right? And something tells you that, and let's say that you have the input x1, x2, and obviously both of these are going to both the boxes, right? This is the one. So you will have, let me call this box 1, this box 2. So you will have a first box input 1, and this one is first box input 2, and this one is second box input 1, and this one is second box input 2, the weights, the resistors. So now you have four resistors as far as I can see, right? And what they can do, something tells you that they can recover these two decision boundaries for you. What do you need to do now? Then you can always take their output. Can we potentially take their output and massage it, for example, right? Produce that. So something intuition. So for example, we can say that if both of them say it's on, let's say that this is the positive side and this is the positive side, right? They both produce positive probabilities. Right? You can put a threshold. You can say that P1, the total probability, the P1 plus P2, the output of 1, which is, let me just call it Y1, Y2. So you can say that the two things, Y1 plus Y2 should be greater than equal to 1, because this is more than 50% Y, 0.5 plus, and this direction for Y1, and this direction is Y2 is greater than 5 in this direction, right? So in this region, you can be pretty sure that no matter what, this condition will be roughly true. Are we getting there, guys? Is this intuition making sense? See, this is a very hand-waving argument that you could play with 2 boxes and maybe 3 boxes, and now this guy just needs to add Y1 and Y2 and then get away with it in some way, right? So to generalize it, we may even put some distortions here. You can put some other weights here, layer 2, let me say second layer Y1 and the second layer Y2. To produce a Y, you may even put a distortion. You might as well, since the shop is only selling one kind of box, you might as well stick it in here and see whether it will be able to recover this. Am I making sense, guys? Is this intuition coming across, or are you feeling lost? Anyone? Did we understand that, guys, what we are saying?
Yes, sir.
It is hopefully easy to understand, right? So what did we do? Oh, we did something very interesting, actually. By putting these 3 things together, we just created our first neural network. And this magic work, and these magic boxes, these things that we are calling magic boxes, in a more formal way, these are called neurons. Our neurons, node, sometimes these words are the same as our magic box. Are we together? They are the same thing. And what we are looking for is a first neuron in which, now what you do is you think of this input itself as a sort of a node in its own right. All it is doing is passing it forward. You say that in your network now, this is your, what is this? This is your hidden layer. Are we together? This is your input. And this produces the output, your output layer. Am I making sense, guys? Anyone who wants me to clarify or is not persuaded by this argument? So now we can generalize from that, guys. So suppose I see a decision boundary, which in my mind I can approximate using a triangle, right? So outside I see blues, and inside I see reds. Now I can guess, just a guess would say that I probably need a hidden layer of how many neurons? Three magic boxes. Three magic boxes. And then I can feed it into this and get my output. X1, X2 will go into each of these. And my work will be probably done. But actually what happens is that this distortion function, this activation function, they are interesting. Sometimes you can get away with less than what you think, because they manage to deform the input quite a bit. You know, whatever the Z they get, so think about what happens. Y is basically this function, this strange function. It's a transcendental function of Z, which is a function of X. Z of X is linear. Remember, we just wrote it. W0 plus W1, X1 plus W2, X2 in this example. But Y does this weird exponentiation, and so it becomes like a sigmoid. It's a distortion of Y, right? So activation distorts the Z input. As far as the activation is concerned, Z is the input to it, and it has managed to distort it, right? And so this brings us some very interesting possibilities. What I would like to do is this theory that I developed this way, let us see if this is really true, if it works. So what we will do is, now we will do an excursion to our website where there are some data sets drawn, and we will use our intuition and see whether we can solve the problem. So what we learned so far is that you can use these logistic units, and they have a very strong physical intuition. You can think of them as a bunch of resistors, variable resistors, and an activation function. So the only things we can change or slide are actually the resistors. We cannot play with the input. We have to achieve the desired output by sliding the resistors, isn't it? The rheostat slider, the variable resistors. And that is a physical intuition of what learning is. Machine learning is all about getting that right, essentially. Moving those weights around, the sliders around, so that the output is what you want it to be. Now, with that intuition, we also take the other intuition that one magic box, draws one straight line as a decision boundary. Another magic box can do another straight line, and then you can put them together and then put it into an output magic box, and now you're done. You can produce what you want, right? The output that you like, if it is V-shaped. If it is triangular, if you see 3 lines, you can do. So let us see if that intuition really is correct. We can verify that. What we will do is, we'll go to our website, a course website, and we will play around with something that I hope you have played around with, which is the, where are we? Where are the fun resources, weekly suggested, fun deep learning resources? I'll go here, and in this, I will go to something called the TensorFlow Playground. Give me a moment. TensorFlow Playground. So here, guys, we have a few data sets. Let me start with this. Tell me if I should make my screen a bit bigger. Yeah, this. Is my screen visible, guys?
Yes.
Right. And so We will,
Better.
yeah, and very helpfully, I suppose, they have made them nice square boxes. These magic boxes, they actually look like boxes here, so which is very good. So look at this data, guys. Blue data, orange data, right? Very close to ours, blue and red berries. So if you were to draw a decision boundary, how would it go? Can you imagine in your mind a decision boundary going through it, guys?
Yes.
Yes, isn't it? And how many decision boundaries you need? Just one, right? How
Right.
would it go? Could someone tell me how you can imagine a decision boundary that will classify the orange points away from the blue points?
Simple linear function.
And how would it go? It would go along the principal diagonal here, sort of like that, right? Imagine a decision boundary like this. So to draw one boundary, how many boxes do you need?
One box.
Just one box. So now you look at this. This is a very interesting thing. See, you are supposed to play around with all of this. And most people come here and they do hit and trial. And they try to mimic or create something. So they'll do something like this. And do you notice that it has drawn a decision boundary like this particular neuron? And you may feel very happy that, see, I have a neural network with one hidden layer, well, two output layers here, that is drawing it so well. But the question to ask is, did we actually need all this, right? Suppose each box cost you $100. You have spent a lot of money here, right? So we will do something better. Let's see what happens if we go just with this. One, do you see that one box will just draw a straight line? Let's try that. Let's start the training. The big button for training is here at the top. And what happens? Does it agree with the intuition, guys, that one box is enough to draw one decision boundary? Right? It goes with the intuition. We could have done it with, if you have done ML100 with me, you know that this is true. Now, let's play a different game. What if the data look like this? I'll let you stare at this data and I'll let you tell me how many lines will it take for us to get this?
I think 2 decision boundaries.
We see 2 decision boundaries, right? So we can't do with one. If we try to train with one, it will get lost, isn't it? Let's try that. Yes, clearly it is lost, right? It's gotten all these orange points wrong. What we need is another decision boundary that cuts across here and separates the two. So let's add one more. 2 boxes. Well, now that we have 2 boxes, let us actually have, it won't be sufficient. We need another magic box here to, we need, where is that? I need to increase the number of layers. And I don't need 2 of these. 1 should be enough. Let's try this. Does this look something that will suffice? Because in our mind, we saw 2 decision boundaries. Is it seems to be going along? Well, not quite. It doesn't seem to. It seems to have still missed it here. And this is interesting because this is sort of an XOR like data set. XORs are always a little bit tricky. So see what happens if I add one more here. And these are the 2 outputs. Is it still looking simple, guys?
It's a decent approximation, yeah.
Yeah, it's a good approximation. And what would happen if I just increase this here and decreased it here? See what happens. It wouldn't do because you need to create this other curve. And so in the second layer, you need to add one more. The first one is just distorting. You need to do that. So this is how you develop intuition. It is important to make the simplest, neural networks. And you can often look at a problem and do that. What about this guy? Look at this data now. What would you say? There's something funny going on.
It needs x square.
Yes. Remember, just a transformation of the input data. And those of you, of course, who have been my students would remember this very clearly. Actually, we don't need x1, x2 at all, isn't it? And actually, it's just a simple decision boundary. We don't need this. We don't need this. We probably layers. Let's try our luck with something simple. But we just feed in x1, x2 square and see what happens. Do you see that the problem gets solved? Yes. So what I'm trying to say is that, if you think about data systematically, you can create elegant and simple solutions rather than just by a trial and error. So what about this guy? This is more complicated. So how many decision boundaries do you see here?
As such, it is similar to x square, but it does have a component of, I think, xy or xn.
Yeah, see, think about it this way. See, if you start here and you put a decision boundary like this to separate these two lines, and we need another decision boundary to separate these two lines, right? We need at least two different decision boundaries. There is a radial function here, but we also have linear effect because it's linearly radiating out. So let's try our luck. We need two decision boundaries and let's see what happens. Not quite, doesn't do it, right? What if we increase it? Oh, by the way, we need an output layer. This is not enough. We need an output layer. Let's start with this. Well, not quite. Now what can we do? We add a few more layers. So what does it take for it to do this business? Do you see how it is wrapping itself around the data? And look at the loss. It has pretty much hit it accurately. Right? So I put a lot of boxes here. Now let's try removing a few boxes and seeing what is the minimum number of boxes that we need to do this. Not quite. If you let it run for a very long time, do you notice here that the training loss is coming down rapidly? It is still coming down and down and down, and we'll probably get it in due course of time. Almost there, guys. Training loss, the test error. So this is a measure of error. You can see it disappearing. And this solves the problem, right? So this is it. One thing you see that no matter what the shape of the data is, if you take, you can always think of a neural network that will solve the problem. So what in reality happens quite often is that people are not so careful. They will not think through the logical aspect of it. So they'll go something like this. They will say, oh, forget the x square inputs. We'll just take these and let us go and add 8 neurons for good measure. So this is one hidden layer. Let's go for it. So you realize that when I remove x1 and x2 square, you are actually removing some amount of information from this, some feature engineering out of the picture. Now, this is still high error, but it will ultimately gravitate to who would like to bet that this will solve it or not solve it? Anybody's guess?
It's hard to solve it because without this square component, drawing a circle is difficult.
Yeah, but this is a point. See, what happens is that these points, when they go in, I have this layer, right? You can, in effect, get the squaring behavior by adding here. Let's do one thing. Now see what happens. I add a few extra layers here. Let me go to 8 here. So what will happen is that because you took the input and you are exponentiating it, you will end up at this layer already with square components, the second layer. And see this. Actually, it's learning a little bit slow. Let me take another.
According to the theorem, it should solve it, right?
Yeah, it should gradually solve it.
Because the theorem says with any number of hidden layers, you can actually approximate.
Yes. The only question is how many of those do you want? Like how many layers do you want and how many neurons do you want in that layer? So it is still, you can see that the error is decreasing, and we can sort of trust that gradually it will get there. It will still have some mistakes, but it will get there. You notice that it is getting there. Now this little link has to be fixed. It isn't, but practically it solved it. Do you see the training error is very, very low now? Right? So you ask this question without the square component. You know, the squaring gives you, the circle is x square plus y square, right? X1 square plus x2 square. Where did that come from? The reason is when this went into this neurons, each of these neurons, and they exponentiated, what did the activation function do? It introduced a distortion, nonlinear distortion. In other words, another way of thinking it is, it produced a lot of higher degree polynomials of each of the input variables. If you expand that function out, you'll realize that all those higher degree polynomials are sort of born along the way. They get generated along the way. You don't have to explicitly feature engineer and feed it into the network. And this is an important lesson, guys. What in neural networks, one of the things we realize is that traditionally we used to do a lot of feature engineering. Feature engineering is still the gold standard, because if with feature engineering and a interpretable model, you can solve the problem, nothing beats it. But if you cannot, if you must use a black box, then some of these, like deep neural networks, they have an internal capacity to discover those features. It is called representation learning, and this was the breakthrough of 2009, and 2006 of Hinton. We'll talk about that as we move along, hopefully in today's lab itself. Right? So I've given you some idea. Now you notice that there are different activation functions, linear, sigmoid, tanh, etc., etc. Generally, ReLU will be much faster. Sigmoid is the slowest. And almost, see, when they use the word sigmoid, they're abusing the language. Mathematically, tanh, tanh is also a sigmoid. What they mean here is the logistic function. And in the deep neural network community, you'll often see this abuse of terminology. They'll often say sigmoid when they really mean tanh. Logistic, right? Because sigmoid encompasses tanh in the strict sense. So that is that. So
Asif, sorry, one question. What does this ReLU look like?
Yeah, we'll come to that. So
Okay.
The activation functions are a topic. We'll come to that today. Huh?
Okay.
What about classification problems? Regression problems. Well, which data set do you want to use? We don't seem to see many data sets, and it is unclear what it is trying to predict. But anyway, I will leave the regression alone. You guys can play with it. But classification, this example becomes very easy to understand. Now, I'll go back to our stuff and ask, classification is all right, but what about regression? Can we argue in a similar way that we can use these neurons, these basic units and their activation, these magic boxes, to create a regression also? And the answer to that, very pleasantly, is yes, we can do that. And I'm going to show you how to do that. Let me take a bit of paper and start doing that. And I'll go a little bit faster now on the argument. Regression. regression. How would you do regression? So think about it this way. Go back to our situation. Suppose you have a function that goes like this, right? So some weird function of x. This is x. Regression would be able to reproduce. So this is your fx. You want a gx that approximates fx. How would you do that? So what you do is you do it, you argue for it piecemeal. You say, you know what? Just as you learn to do integration, we'll break it up into tiny little stripes, this function. And what we will do is we will find if we can create an approximator for, obviously this function cannot move back, it has to move forward. So this. So let's look at this one little block, right? And this little block. Suppose I did these functions. I could produce a function that could produce this, and something that could produce this, and something that could produce this. So what will happen is this would look like this, this would look like this, this would look like this. So what will happen is you will end up with a function that goes, you see that you can approximate it if only I could, for example, reproduce one pillar using my magic box somehow. Isn't it? If I can reproduce this pillar at, let's say, this location, ith location, then I can create a lot of those pillars. I just need some way to produce and pay attention to this argument, the SI part. So how does the SI part look? Let's look at this. The SI part, and so this is the location at SI. We want a function that stays quiet, but just around this achieves this height and goes back. So let us say this height is HI. So suppose it produces only this much, but at all other times it is 0, right? So in other words, its value is like what people call a step function, like this. And then it suddenly achieves the value of this function, and then it again goes back to 0 and continues as 0. So suppose I could write this function using my magic boxes. Then all I need to do is I can take those mechanism and stagger a lot of those things horizontally, and I'll be done. So the question is, how would I do that? Well, it turns out that if you look at this function, something that goes like this, let's look at it. It is called a step. The step is, if you look carefully, it sort of has a feeling of a sigmoid. So, you know, you have a S sigmoid. What happens if you take this sigmoid, and sigmoid goes like this, isn't it? What would happen if you sort of squeeze the sigmoid tight, squeeze it so that it begins to look like this. And how would you do that? Well, there's a little bit of a machinery here, but I'll tell you the solution. Remember that we said we do it based on the inputs, right? The X and the weights. What we do is a weight bias term, the weight W0. Let's say that this function is W0 plus W1X, and only in this region, we do a sigmoid of it. You know, there's a weird distortion of it. So what you do is, if you make this big, by controlling the slope, or rather this part, W1, you actually control how quickly it rises, right? How much it begins to look like a step function. It's just a mathematical property. And what in the world does this guy do? It turns out that when you decrease it, the more negative you make W0, the more it moves back and forth. So in other words, this curve along the axis, if you make W0 more negative, it will move back and forth. Right? This is controlled by W0, and the steepness is controlled by W1. It's just a mathematical property. Right? Just take it as a fact that it is true, and we'll see an illustration of it in just a moment. So now comes an idea. Looking at this, it looks like the first part of the slope. Would you agree, guys? If I'm writing a function that looks like this, one part I can get by one of those magic boxes, box 1. I just need to configure it properly. Do you agree with me, guys?
Yes.
Right? It is straightforward, right? I can use box 2, and then I can use another box to produce this other part of it, box 2, right? All I need to do is, instead of x, I just put minus x, right, in your function, and then I will end up with a sigmoid like this, and that I can squeeze into a function like this. So what we conclude is, by, again, somehow the magic of 2 boxes. Are you following the reasoning, guys? I just made a pretty strong argument here. I'm saying by using 2 of these magic boxes somehow together, right? And this solenoid's built in, sorry, not solenoid, this resistors built in, I can use this combination, X goes to this, and what I can get is, in effect, an output node Y, which will look exactly like this. This box will produce for me this result exactly like this, right? Will produce this for us. So far, so good. So you need a pair. You basically need a pair of boxes. Make one tiny part of the curve at SI, at this location, right?
So, sir, why a pair is needed? I was thinking that only one box is needed.
Oh, see this box. So listen, this box will produce this, and then right shifted, this box will produce this.
Oh, I see. Okay.
And so
Right.
these 2 boxes put together will produce
This one, step function.
Step function. It's the beauty of it. And so now can you guess, how do I create this entire thing? How do I recreate the entire function? What do I need to do?
Add the same thing again and again.
Whole series of
Series.
magic boxes.
So for each of these locations, just go adding pairs of boxes. So what I can therefore do is I can do, just build them in pairs. I'll just put dotted lines here, and then another pair, and another pair, and you can keep going, arbitrarily, as many boxes as there are. So suppose there are K, you broke it up into K parts, right? So K regions. Then what happens? You just need K pairs. K pairs. And so with K pairs of boxes and this input, and again, do you see the beauty of this argument, guys? Right? And then you can play with this. You have it. And so what do you see? With a single layer, you can approximate any function you want. Now we have made this argument in 1 dimension. It's easily generalizable to higher dimensions, but we won't do it in the interest of time because I want to move forward. Do you get this argument? This is a fairly elegantly made argument, and it is made in Michael Nielsen's blog. So that is the reading assignment for today. Now we'll walk over to that blog and we'll try this out in real life. And then I'll show it with some code. We'll actually do that, verify that this isn't all a game. This is real life. It actually does happen. We'll verify it in code. Does that sound like a plan, guys?
Yes.
Let's do that. So let's go back to our educational portal. Where is our educational portal disappeared? Okay, needs to be resurrected. Yeah, go ahead.
You mentioned that we are going to have k pairs of boxes, right? Does that mean every pair is enclosed in a hidden layer, or the k pairs in together is in one hidden layer?
Sudhir, your voice is coming with a lot of distortion.
How about now?
Absolutely clear.
Okay, so now my question is, I was just going over the previous example which you explained, for the k pairs of boxes to implement those step functions, right?
Yes.
So does that mean we are going to have, k hidden layers, or?
No, one hidden layer with 2K neurons in it. Remember, this is one hidden layer. Let me go back.
Okay.
To this. See, one hidden layer, but suppose I make K regions. Suppose the number of regions here is K. K regions are there. For each region, I need a pair of boxes. And so with 2K boxes, twice the number of regions, I will be able to approximate this function in a single hidden layer.
Okay. So, or can we take that hidden layers as, the dimensions? If it is 2D, then it is one hidden layer. If it is 3D, it will be two.
It doesn't work like that. It doesn't matter. See, that only affects this part. Suppose you have 2D, 2D, then this will come out. This will also start shooting off inputs to these. Right? This is how you go with 2D, but that doesn't work. The hidden layer is, in a way, unaffected by this. What happens is that your argument is essentially correct in 2D because these are surfaces, right? You need to be more careful. The number, it is not just 2K, it increases now.
Yeah.
You need a lot more.
Okay.
But you can do that. Right?
Okay. Yeah.
The reasoning remains the same, but you just have to do that. So now let me take here, guys, so guys, by now you must have realized, I hope, that there is a lot of information there on the course webpage. So please do try to come to it. Now I have created a section for today's topic, which was neural networks. Now, activation function I introduced to, I didn't get time to do gradient descent. We might not, actually, so we'll keep it for the next time. So we'll go to this, a visual proof that neural nets can compute any function. Let's see, is that true? So you see this thing, let me make this. This is a reading material, guys, for this week. Please read this very well written chapter in Michael Nielsen's online book. It's a short book. Each of the chapters are, once you understand the concept, you can just glance through and I've explained everything to you. You'll be pleasantly surprised that now when you read this chapter, you'll find it very easy to understand. Right? So he's arguing for what I'm talking about. Now you can read through this, but I'll go down. And at some point he shows, yes. So you see that this is a very peculiar function, right? Now, how do we approximate this function? Look at this. Just look at this neuron. This neuron this is one magic box, right? X goes into this magic box. And when it goes in, what comes out here at this particular point looks like this because it gets distorted. Now let's play with this. See, as I move this B, do you notice that it is moving to the right or to the left? Okay, let me start with the weight. See what happens when I increase the weight. Is it beginning to look like a step function now?
Yeah.
So that serves a purpose, right? It shows that it does begin to look like a step. And now where is this located? I can, you see, by decreasing remember this was W naught in our notes. Do you see this? By changing the value of B, I can decide where is this positioned. So by now you get the idea that we can play around and create a little bit, one little region of the function we can approximate using a pair of these, and we'll see that in a bit. Here's a little video in which he shows. This is exactly the same thing that I showed to you. Then, what about the other part? The step function is not made. At this moment, it's just step up. It doesn't look like a tiny region. So we need to do the second part also. And so again, that is what he explains. So now look at this. Now he has taken another box. Well, if you want to go up, here we are. So see what happens if I decrease the weight of this. Does it now look like one of our regions? Guys?
Yes, it does.
It does look like one of our regions, right? And so you can play around with this, right? And then you can expand this, you can contract this, you can play around with it. So by now you're getting the idea that using a pairs of sigmoids, you can emulate regions. You can even play around with different shapes and so on and so forth. You're beginning to get that idea. You can even go negative and so forth. So that is the point that is being made. Right? And please do have fun with this blog. It's a really lovely blog. So now you notice that using pairs of it, you can play around with it. So what happens? You see this. So do please play with it, and it will give you an idea of how, for example, this function is being approximated gradually. And so when you look at a complicated function like this, the idea is that by playing with that, you'll be able to approximate it. So now what I would like to do is that show you this thing in real life with code. So in your code, you will see, and I'll upload this for this week's lab. I will show you this thing. Are you guys looking at my notebook now?
Yeah.
Yes.
Is the font big enough?
Yes.
Yeah. So for you to play, what I have done is I've created a simple class for you, universal approximator, right? And what your job is, just imagine, think of some kind of a function. So this lambda expression, let me explain. This is a Python syntax. It basically says that X gets mapped to this. This is as close to math as you can be in code. Does it look like that? X is getting mapped to this function, right? X goes in, out comes this thing, right? And you can put whatever you want. What you do is, and I won't run it, you have the approximator. I made it very simple for you. So first, what do? Whenever you have a model, we need to train the model, isn't it, guys? Remember, the first step is you need to train the neural network. Then you need to evaluate the neural network. And when you evaluate, one of the easiest ways to see how well it is looking at the correlation between Y and Y hat, prediction and reality, how correlated are they, right? So this is what it is doing. And I could run it. Do you guys want me to run it from start? Or we're a little bit low on time. Okay, let me, so let me just stay here. I want to cover one more topic. So what happens, do you notice that, how does this curve look like? This is of course the sigmoid looking curve. Now, if you look at this curve, let me show it to you in a little bit more magnified way. Look at this and look at this. Do you see that there are imperfections here? Do you see little imperfections in the curve? Look at this region in particular. I don't know if it shows through on your screen.
Yes.
Not as smooth as this one, but it is still a pretty good approximation. Would you say that, guys?
Agreed.
Right? Pretty good. And let's look at the correlation. The Pearson correlation between the ground truth and prediction is 99.9984%. Right? For all practical purposes, you have a very good approximation to the underlying ground truth. Let's try something else. What I did is I created a weird function. I put this sin x also into it. And then I trained it. I don't think I have run this. And when you run this, okay, I'll leave this to you to run it. In my case, why is the running part not showing up? Give me a second. I don't know what just happened. Okay, for some reason, it has gone into a read-only mode. Oh, it was hiding here. Okay. I have to run it from the beginning. Then, let's see, it is running. Do you notice that it's approximating it gradually? I run it for only one epoch, which is usually good enough for this one. And the accuracy is 99.95%. The plotting, I just plotted exactly the plot we want. Now let's try with this weird function. This weird function also is trying to approximate it. Oh, I didn't plot the figure, but you can plot the figure. I'll leave that to you to plot it. 99.98% accuracy. Well, pretty good, you know. Imagine writing some very strange function like this, and then having a neural network approximate it, you know, generating data from this. I took another one, a sync function. Those of you with some background in hardware would be perhaps in love with this function. It's very common. What does it look like? So I won't run it because it will take a bit of time, but not much time, but this is it. So now I made a curve that looks like this, and look at this. This thing has been able to approximate that also. So then I thought, let's go crazy. Now, this looks really confusing, isn't it, guys? Would you agree that this is, how many of you would like to compute this by hand? Any takers?
No.
Well,
I called it too many signs.
It will be very frustrating.
Yeah. So all you have to do, by the way, guys, play with this. And the only thing you have to do is either define the lambda function as a lambda or actually define it as a function. Follow this code the way I've written it. The rest of the 4 lines of code are exactly the same. That's why I've simplified it so you can quickly play with it. So the original function is like this. Do you notice that? Right? And what the neural net does is this. And it does it in only 2 epochs. If I run it for more epoch, it gets better, but I won't do that now. Here it is 98.46. So you can try running it for 5 or 6 epochs. You'll notice that it begins to pick up on some of the perturbations here. But would you call this a pretty good approximation of this crazy, crazy function?
yeah, smooth. Where do we get this notebook? I don't think it's in the original. Is it newly posted?
Yeah, I will post it now.
Okay, because I was like, where is that?
Yes, it is week 2, is the week 2 work, is the week 2 node. I haven't done it.
So, so the functions, those graphs, is there some data it's working on, or is just directly doing it on the functions we are defining?
Yeah, so if you want to look at the code, actually, what I do is from the function, I generate the code. Since you asked the thing, what happens is you can, if you go and look at the approximator, univariate approximator, you will see that what I do is, do you notice that if you give a function to the input, I generate the data, you know, create the data. Do you see me? Create the data.
Yes.
That is it. So the idea is that obviously you won't know the function in real life, but you will have the data. And the point of neural networks is, irrespective of what crazy function produced the data, the universal approximator theorem guarantees that you will come pretty close to it. Isn't that a most remarkable result? How many of you are impressed with that?
Yes.
Yeah.
Pretty impressive. And now you can sit back and say, perhaps we are beginning to understand, why do neural networks work at all? And why do they work? Why are they so versatile? And why are they so amazingly effective? So see, you know, we are starting on a journey of deep neural networks. It is one of the things we miss. Your textbook, for example, your lab textbooks misses. But at the heart of this subject, it is always worth knowing what drives the engine. So now you're getting some clue on what drives the engine. So we have 15 minutes left. The one thing I wanted to cover today are the activation functions, all these distortion functions, but I don't want to do it in a hurry because as the old British saying goes, hurry spoils the curry. Let's not do that. We will do it carefully next time, and gradient descent also next time. This took a little bit longer than I thought, but I hope you did find it gave you some idea of what this subject is all about and how it really works. Next lab is, of course, nothing to do with theory. We'll completely focus on actually building practical neural networks and solving practical problems on Wednesday. Right? But with that thing there, guys, I would like to emphasize, please do give me feedback. This is the feedback I received till morning, because the feedback, let's look at the feedback, because the feedback helps me decide what to teach over again. So if I know that some topic is not clear, so we seem to be doing reasonably. Now, where have we, yeah. So it says, understood most of it, though some clarification needed. 4 of you felt like that. So what it means is I need to be more careful, and I would love for you guys to speak up. When I'm not clear, stop me. We will do it. We'll do it in the extra session on the Saturday, but one way or the other, I want to make sure that we clarify it and you understand it, because this field is all about understanding some very simple ideas. That's all it is.
This is very good. You should probably include at the end a little field for a text comment.
Oh yes, excellent idea. Why don't I do that for this week's feedback? I will do that. Nice. So, so here is interesting. The pace is a bit faster than is helpful. Perhaps we need to slow a bit. 3 of you felt, 1 of you felt we need to go a bit faster. But most of you felt that the pace is about right. So the people who are finding it a bit slow, and 3 of you are there, I do apologize. You know, part of pedagogy, part of the whole educational processes, you know, what was the old slogan? No person left behind. You always make sure that you're carrying everybody with you. At the same time, you know, for people, so, but for people who are finding it fast, take it as a responsibility. Don't hesitate. Immediately stop me. If I'm going too fast, I would love to slow down. See, remember guys, I said that this is 6 weeks, but in reality, we'll take as much time as is needed to cover part 1. And we'll keep, as you know, every single workshop in the past, we have gone longer than was initially planned, but we have learned it well. And I would like to do that. Nisa, go ahead.
Yes, so Asif, if you could give a 5-minute break, right? So after an hour, maybe just give a 5-minute break and then continue for another hour, because sometimes it goes an hour and a half.
Oh yes,
yes. So that even a 5-minute break will help us to kind of, you know, again, refocus. So that's one of my feedbacks. Otherwise, it was great.
I agree with that.
Yeah. Okay, I'll remember that. And if you see me get carried away and lost in the subject, please do stop me at the hour interval. Okay. Just say that might be a good time to take a break. Don't hesitate, please. Sometimes I get lost in the topic. So this is good. So this was something a bit worrying. Auto ML, I clearly have done a very poor job. Only less than about half the people feel that we didn't do a good job with Auto ML. So I'm going to repeat it, guys. I'll go deeper into it and I'll repeat it. Of course, this was just an intro. I'm going to repeat it later, but if time permits, even the introductory part, I'll try to repeat it this Saturday or at some point. Whatever is not clear. And the transfer learning has had a similar effect, though I'm hopeful that this is easier. We'll pick it up as we move along, hopefully, or otherwise we'll do an extra session on that. Right? And Jupyter notebooks, are you able to follow the experiments? So here there was a very useful feedback. It says, I need to add more explanation in the notebooks. So I would love to do that. Could one of you elaborate what would help? Like when you look at a Jupyter notebook like this, how can I, oh, sorry, not this. When you look at a Jupyter notebook like this, give me an idea. How can I help you with more Maybe in every section, I need to add more text and more explanation. Is that what you guys are looking for or something else? Should I comment my code more?
Can you add more comments to explain the code, like some?
In the code itself.
Yeah.
We do that.
I think, Asif, from my perspective, commentary in your saved functions, the functions which you're calling in this main code, I think that would be helpful because the code, I feel it's understandable, but some of the functions which you have created and which you're calling, some of them are like difficult to follow, especially if you're not very familiar with data structures and algorithms.
Oh, yes, yes. See, guys, let me be clear. At this moment, right, to go back to the code behind and understand it, I ask you to go take a tour of it. Don't expect to understand it yet fully. It is meant to be difficult, but the reason I wrote that code is so that your notebooks are simple. Your goal is to understand the notebooks. Understanding even some of the code is a stretch goal, guys, at this moment. But I will try to make sure that there is more documentation in the source code itself. I'll remember that. Huh? So, all right, guys. So that was one feedback, and where are we in the feedback part? Yes, and overall experience seems to be more or less positive. Anyway, guys, so we will review our feedback every week. It will help me, guys. It'll give you what it is that will get you best through the course. So let us summarize where we are. Today we gave pretty much the whole day to a couple of topics. The topics were, and let me do this. I seem to have written all over this blackboard.
Just wanted to know what are the chapter numbers that we've covered today, just to go back and review in the textbook.
I will post it in Slack right away.
Okay.
I would suggest, okay, so let me remind that what I would suggest is don't start with the textbook. That textbook is a high bar. Huh? Now that you have listened to the lecture, you'll understand it. But in the textbook, the universal approximator is mentioned very succinctly, if at all. What I want you to do is do this one. Where am I? Deep learning fundamentals. Okay. Do you see this section? Neural networks are universal approximators. By now, I hope I've convinced you of this fact that neural nets are universal approximators. So guys, those of you who like it visually as a video, watch this Michael Nelson's video. Those of you who like to read it, go read the Michael Nelson's chapter, online chapter. This is your easiest start and a review of what we have done. You'll see that you do. So he does it only for regression. He doesn't explain the classification part the way I explained. That is not there. Right? So that you can just look from my video. That may be unique to me because I don't think I've seen that sort of explanation anywhere. So for that, just go back to my video. Huh?
Our portals are going to be updated so they look like that.
I'm sorry, please say that again, Kate.
Is our portals that we see going to be updated so that we have these links? Because I don't see that right now.
No, these links are there. Please,
They are there. Yeah, I can see it.
Please refresh the page.
Under the...
It's further down.
See, Kate, I'll give you a hint. You see this navigation, right? Always use the navigation. It is either on your left or your right. Most likely you guys have it at in this way, right? So because it is a long page, you know, seems like an infinite page almost. What I would do is just go to the table of contents and search for this. So you will notice that somewhere here, the neural networks are universal approximators, right? You can go click on this. That is one way to do. Another way is, you know that the word approximator is there in this page. So you can just search for the word approximator.
Okay.
Right? So,
I see it. It's things just get pretty buried.
And then there is another blog actually from Christopher Ola. I have interacted with him a few times. He explains, and this is of interest to those of you who want to understand how activation functions distort the input manifold, the input. So what is a manifold? You know, you'll see this word manifolds and topology, right? Topology is the shape of things. Manifold is, well, okay, think of it, the cloth, right? Imagine a nice silk cloth. Now, in 3 dimensions, you can think of it as a cloth. Now, what does a silk cloth have a property of? You can't wrinkle it up. It will always be smooth and nice. Do you agree, guys? When you look at a silk cloth, imagine a silk sheet crumpled up on your bed. No matter what where you look at it, it will have smooth undulations, right? Smooth curves and bends and so forth. So things that are smooth geometrically, ultimately that's a function. Now again, think in terms of function. In 3 dimension, that your silk bed sheet with all its curves and undulations happens to be a function. And in fact, it may be a regression function, right? If you relate it back to our work now. So maybe a new way of looking at bed sheets and blankets. But it has a quality. It has 2 qualities. First is, you don't find sharp edges there. You don't, unless you iron it, which I hope you don't. So it will not have points meeting very sharply at any point, or lines, ringed creases. You won't find creases there. The second good thing that you find in silk sheets is that no matter how much you undulate it, if you look locally at a region, imagine that you're a little ant, right? And little ants, by the way, have you guys seen ants coming into the house? Recently, I've seen ants coming into my house. And so this is very real. I saw an ant on a sort of a blanket sort of thing I have, and it was roaming around with it. So think from the perspective of an ant. Will the ant, which has little eyes and can only see in front and the regions around it, will it know that the sheet is crumpled? What will the region, what will the world around the ant look like? What will she see? Anybody would like to guess?
Hills.
No, it will see just a plane, because everything looks green. So a kid going through even lower space, right? A tiny ant, or think of a dust mite. What does the blanket, or wherever that,
Dust mite, yeah.
It is flat. The world is flat to that little insect, isn't it? So these surfaces that have these 2 properties, that locally they look flat. Flat means, to use a more technical jargon, they are Cartesian. They basically look like Cartesian spaces, R square, R cube, and so forth. But let's say R square, plane surfaces, and that don't have creases. These things, there is a fancy word for it that mathematicians use, roughly. These are called manifolds. Obviously, you need one more property because of the undulations. One ant's, map of the world may be different from another ant's map of the world, because ultimately the sheet is curving around, and it has undulations. So you need a way to sort of reconcile the regions that both of them are seeing if these ants are close to each other. So you have to have a sensible way to translate from one ant's map to another ant's map. So long as you can do that, and some mathematicians do worry a little bit about that, but roughly speaking, on a sheet of silk, you can do that if the ants are smart enough. So that is a manifold. That's what a manifold is, literally. And we can say this whole thing in much more fancy mathematics, but roughly speaking, that's what a manifold is. So you realize that regression is essentially searching for that line or curve or plane. All of these are examples of manifolds embedded in the data space, in the feature space. Likewise, a decision boundary is nothing but, again, a manifold embedded. So in many ways, you can say all of supervised learning is a search for these hidden manifolds. Right? So with that explanation there for manifolds, and the structure, the shape of the manifolds are the topologies. How do they look, kind of a thing. So that's a by the way, very hand-waving argument. So if there's any mathematician, you may get a bit annoyed by my oversimplification. Be that it is, let me take you here. So he talks about this, Ola, in this lovely blog of how neural nets and their activation function, they deform the space, the input space. So you see that, how the layers that come afterwards, they see a very distorted view of the original input as they come along. Right? And so I would highly recommend you to read through this blog. It's very useful. Are we together? So these are the two readings and a video, or alternatively a video, that I would encourage you to do, guys. So going back, and then we will do the lab next time. And then tonight I'll give you the theory reading material from the textbook, the main textbook. There isn't much. And then we'll talk, it has a discussion of activation functions, etc. But I'll discuss the activation function in much greater detail next time in theory. And next time will be devoted just a little bit of time to activation functions. There's not much. We covered the main idea, but I have to just show you examples of it. But next time we'll deal with, next week theory will be gradient descent and backpropagation, the concept of backpropagation. But we won't wait for theory to develop, the fundamental ideas to develop. In Wednesday, of course, we'll steam ahead and start doing practical things, build a real neural network and understand PyTorch code. So Nisa, to your point that my code, right, is a little bit hard to understand. Let us hope that gradually it won't be hard to understand in 2 more weeks.
Okay. I have a question, Asif. During your Saturday session, can you take an example of one of your source code and probably help us how we can learn it by ourselves, have stops and stuff like that?
All you have to do is show up. Those of you who showed up on Saturday, remember, at the end of it, I did whatever you guys asked. It's a carte blanche. Come and ask for it.
Okay.
Right? But I will definitely do that if you're around.
Yeah.
All right. So guys, I hope you're aware that all the videos are here. We had 7 sessions in week 1. 2 of them were necessary sessions, Monday and Wednesday. There were 5 optional sessions, all of them on Saturday. I hope you're aware that we have videos of all of them. Here, look at it. The first one is a workshop administrative year, the rules and regulations, which was on the Monday, the first half. Monday, second half, we did an overview of deep learning. Then we did the lab on Wednesday, and these are the Saturday sessions, 4 sessions on Saturday. We reviewed the 2 quizzes, then we did a beginner's introduction to Python, and then it was a free-for-all, like whatever. It was a open door, clinic hour, whatever people asked for. We will repeat this pattern as we go along, but there is one thing, guys. This week, I have added an extra thing. We are going to read papers, but because we are still starting on, I have not talked about Christopher Ola's blog, this manifolds and topology blog. Please read it. This is a stretch goal. It's an optional. If you're just entering machine learning, don't. It might be too much for you. If you want to read it, and discuss it, then do read it, and we'll discuss it on Sunday at noon. So it's totally up to you if you want to go that far. But if you do, we'll have a guided walk through the whole blog, and I'll explain things. All right, guys. So with that, I will conclude for today.